Alright, hell yeah. We got statics, and we got problem number 6. Let's get into it. And, yeah, I'm going to work on a couple things. Hopefully my penmanship gets better. But, alright, so at the end of the day, they just want to know the units of K. You know what I mean? Here's K. Here's acceleration. This is gravitational acceleration. This is a distance. And this is a force, like a weight. You know what I mean? We can read it. In a certain application, the acceleration, A, and the position coordinate, X, are related. So that's kind of cool. You know what I mean? If you got something, like if you drop a rock off of a building and you got measurements on the building, and you're like, huh, every time it moves a distance, it seems like there's a change in velocity. You know what I mean? Its velocity is so... in this case, if you drop something, A is just constant. But you know what I mean? If you drop something in water, you know what I mean? The velocity is 0 right here. But by the time you get down to here, the velocity, might be higher. And so definitely dropping stuff in water, the velocity is going to be a function, or the acceleration in water, the acceleration is a function of the distance. Because at some point in water, you know what I mean, you get no more acceleration. Acceleration is 0, acceleration up here is going to be max, and at some point, you're just going to hit terminal velocity in water. But anyway, I'm just saying that in general, things are kind of related, and we look at that, you know what I mean, we take that into consideration in physics. So anyway, so it's related by this equation, where g is the gravitational acceleration, k is a constant, w is the weight of the particle, and show that this equation is dimensionally consistent if the dimension of k is f over L. And then the other thing is you should always throw in a 0. You know what I mean? At position 0, the acceleration is 0. Okay, cool. And then at position like 1 meter, you know what I mean, 1, the acceleration is gravity times this constant divided by w. You know what I mean? So anyway, and then the more that you go distance-wise, this just explodes. You just get a ton of acceleration because it's going to keep going up. I guess linearly. You know what I mean? You get a linear relationship. All right. So at the end of the day, I guess to do this one real fast, is that you have acceleration over here, but you have acceleration right there. So all this stuff has to kind of cancel itself out, if that makes sense. That's one way to look at this problem. And so let's take a look at this. And so you have a force downstairs, and then you have a distance upstairs. Let's say, you know what I mean? So this is your F and L. Well, F and L, show that this equation is dimensionally consistent if the dimensions of k is f over L. Now, does that make sense? Because if we go times f over L, all those cancel. And yeah, this has to be dimensionally 1. You know what I mean? This is dimensionally, this whole thing has to be dimensionless, because the dimensions on acceleration over here have to match the dimensions on gravitational acceleration. Now, let's just do it another way. Acceleration is feet per second squared. Cool. And that's going to be equal to gravitational acceleration, feet per second squared, times this k, we don't know k. You know what I mean? Times this distance, let's just say it's in feet. And now divided all by weight in pounds. Okay, so now let's just start adding things up. Or just on both sides, you know what I mean? Let's just do it one more time. So you got feet over second squared is going to be equal to feet squared divided by second squared times pounds. Now times by this k. Now there's a couple ways to do this. You can just be like, you can just isolate k. I think that might be the easiest thing that most people. I mean, just consider this a variable a, a variable b, and then this is your variable c. Now just isolate variable c, and you're going to get k is equal to, you know what I mean? So you got to take all this stuff upstairs, and then this downstairs. So you're going to have k is equal to feet bring all that stuff upstairs, and then divided by seconds squared, bring all this downstairs, feet squared. Okay, so now you can just easily start canceling stuff. Seconds cancel. There's 2 of these feet, there's 1. So this foot cancels, that gets rid of that. And now you're left with pounds, feet. Okay, and in general, that's going to be force over length. Okay, and isn't that what we got? That's exactly what we got. You know what I mean? So we're kind of done. And we can make this a short video, but we're going to do one more thing. Because this comes up a lot, this constant, and it should be your best friend. There's a lot of things in physics, science, where you're just like, why does something like that mess with your brain? Because the force of a spring is just kx. Now this should be the simplest thing in the world, but it's just, for whatever reason, it makes your mind just blow up. And let's do the same thing. If dimensionally force is in newtons, and we don't know k, but we know x is in meters, you know what I mean? What is the dimensions of k? Well, and then, so the other way that we can do this problem, we'll just do it like this. You know what I mean? You can treat k as a variable, c, a, and b. Isolate c over here, so you go k is equal to newtons divided by meters, and I just did that again. But the other thing you can do is be like, hey, what do we need over here that's over there? So we need to have newtons. K has to have newtons on top, because we got newtons on top over here. Now, there is no meters over here, you know what I mean? So we have a meter over here, so K has to also divide out this meter. That's the other way of doing this problem, you know what I mean? So one way that I think is non-obvious that people don't do is actually this way. It's just like treat this like a variable, get all those other components of the units on the other side, you know what I mean? Because the take-home point here is, I don't know, the units are the equation. I mean, this is 100%, especially if you have a constant that you know what I mean? The constant will have a number, but everything else is just, you know, the units that you, anyway. So yeah, so let's get back to this one. This is the spring constant. So you have, so this is the value of a spring constant. It's newtons divided by meters. So if your spring constant is in units of Newton meters, you know what I mean, then this should give you kind of a lot of information. It says, hey, if I give you a distance, if I give you a meter, you can spit out newtons. You know what I mean? So that's kind of cool. So if your spring constant is in the units of Newton meters, you know what I mean? This gives you a clue that, hey, all I have to do is give you meters, and you're going to spit out newtons. It's the same thing as density. Density would be like, you know, kilograms per meters cubed. Well, cool. You know what I mean? It sounds like if I give you meters cubed, you're going to pop me out some mass. You're going to pop me out how much mass that, you know, whatever is in that volume. Same thing here with these constants, you know what I mean? It's another way to look at what constants are, and hopefully you can kind of turn them into your friend, you know what I mean? Because this should be the simplest thing in the world. I mean, basically, if you have a spring, you know what I mean, at a playground or something, and it's just dangling in space, and you got 2 people, one weighs twice as much, the smaller one pops on, moves the spring down to there. Well, the bigger one pops on, going to move the spring down to here, double the distance, you know what I mean? Because it's linear related. This says, hey, the force is due to the distance that the spring gets pulled. Perfect. That's kind of it. You know what I mean? And if the spring gets pulled like a tenth of a meter, you know what I mean? 0.1 meters, like that doesn't mean 0.1 newtons. You know what I mean? That's why we have a spring constant. That's why, you know what I mean? For every, if a person weighs, you know, 600 newtons, the spring constant for this, then we could just do it. Let's just plug in the equation. F equals kx, and we said we have 600 newtons, and we pulled this thing down 0.1, and we have k. Well, I think the easiest thing to do is just separate the variables. So we're going to do k is 600 divided by 0.1. That's the same thing as multiplying by 10. And you're going to get a spring constant of 6,000 Newton meters. So you have a spring constant of 6,000 Newton meters. I gave you the meters, 0.1 meter, and then you spit me out the newtons. This person weighs 600 newtons. You know what I mean? And then the other person, if they weigh half as much, it would only move this thing not a tenth of a meter. It would be 0.05 meters. You know what I mean? So it would be, I moved it 100 millimeters. There you go. And then the other one would be 50 millimeters. So 50 millimeters, 100 millimeters. So that's kind of in a jiffy, at least one application of this constant, and how even the constant, if it's got units, the constant is the equation. You know what I mean? Because whatever the constant is, do I have any more time? I mean, hell, we got another sheet of paper, so let's just keep rolling with it because I'm kind of curious about one. Because usually no one likes the constants because it's just, it seems like a made-up number, and then it's got all these units that might not make sense. So Kepler, force of gravity, gravitational constant, mass 1, mass 2, divided by radius squared. Now, same thing. What's G? Well, look at this. You got a mass right here and a mass right there. And these are in kilograms, right? And then you got a distance here in meters, and then you squared it. So, you basically got kilograms squared meters squared. So just real fast, what is G? Well, and then you got to spit out over here newtons. You know what I mean? You got to spit out a force. So G has to have the force in it, so it's got to have the newtons. And it can't have kilograms, so it's got to divide both those kilograms out, kilograms squared, and it doesn't need any meters, so it's got to cancel out those meters. So just within a jiff, we did and I think this is for another problem actually. And then if you use F equals ma, and this says that Newton is equal to kilogram meter per second squared, now we can actually, we can throw in, we can get this whole thing in terms of newtons and this whole thing in terms of mass. So let's do that. Which one do you want to do first? Maybe let's do I don't know which one's harder, but we already have newtons here, so let's figure out which kilograms is. Kilograms is just Newton divided by, keep your penmanship good. There you go. All right, let's do them both. So we got G. Throw in this N. You got if you throw in this for N, you got kilograms meters per second squared. You're going to throw that right into that slot. So you got kilograms meters per second squared times meters squared, all divided by kilograms squared. Well, it looks like, yeah, I guess this works. It looks like you're going to get 1 kilograms downstairs. So we're going to get 1 kilograms downstairs. You're going to get meters cubed upstairs, and you're going to get seconds squared downstairs. Perfect. Okay, so that's it. We did it. Now let's do it with throwing in this for kilograms. So you're going to have G, newtons, keep the newtons upstairs, meters squared. And now we're going to throw in newtons squared downstairs. Divided by, that's the same thing as multiplying up here, by meters squared seconds to the fourth. So, because we got to square it, so I already did that. So anyway, now you're going to have newtons downstairs, meters to the fourth upstairs, and then seconds to the fourth downstairs. Cool. So here is kind of like 3 ways to write the gravitational constant. You know what I mean? So there you go. I think this way makes the most sense because you pop out a Newton and you had 2 kilograms and you kind of got to cancel those kilograms, cancel the meters. So honestly, this one for me makes the most sense, but you'll probably see it like this. Well, I think you'll see it like this in SI units, and I think you'll see it like this, feet to the fourth divided by pounds, seconds to the fourth. I think you'll see this in U.S. customary units. Don't quote me on that. But I think we're getting kind of ahead of ourselves. But this is good because it totally relates. And I think my time's about up on this one. But hell yeah. Thanks for joining me, and let's do another problem.